Right. Welcome back to this session. Thank you for joining us. I'm now continuing with your functions and graphs under transformations. Right. I looked at vertical shifting, which was the effect of Q. When Q is positive, the graph in the previous session, it went up. When Q is negative, the graph will definitely go down, right? I'm still continuing with transformation of functions, and allow me to take you to the board so that we can start. Today, I want us to look at horizontal shifting, taking the graph either to the left or to the right, and I'll also move to your reflections, which will mark the end of this session. Okay, thank you so much. Let's turn to the board and unpack this. Um, Transformation of functions, right? For us to deduce a rule, we need to learn from how graphically this is going to graphically on whatever is going to happen, then we generalize it and take it to our functions. Okay, right. Transformations. That's our topic. Transformation of functions. Right. I'm going to be looking mostly on what horizontal shifting. Horizontal shifting, which P is responsible for our vertical horizontal shifting from our lower grades. I'm going to quickly look at an illustration. Let's look at an illustration. Right. I'm going to draw right the following functions on the same set of x's. Right, the first one x equal to x squared. I'm basically going to use the same illustration. Then the second one, it is going to be equal to what? X plus a 1 all squared. Then C, I'm now going to look at h of x, which is equal to x minus 1 all squared. Right. Now, if you look at this, I'm going to start with the graph of f of x as usual. Allow me to do a table of values. Right, I'm going to draw using a table of values, just like what we're doing in our lower grades in grade 9 and grade 8. Right, look at this. Look at this. Okay, right, there you go. This is going to be like that. Join that one downwards. There you go. Right. Um, I'm also going to use a scale from negative 3. I'll say minus 3, minus 2, minus 1, 0, 1, 2, then 3, something like that. Okay, right. Okay. Right, that's your table of values. We want to use this table of values to deduce or to come up with the graphs and how they will look like. This is x. So the first function that I'm going to plot is f of x squared. Right, now f of x equal to x squared. Right, I'm going to fill in these values. Negative 3, plug it where there's x squared. Negative 3 all squared, that will give you 9. Negative 2 all squared, that will give you 4. Negative 1 all squared, you give you 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. Then 3 squared is 9. So I'll come now to my Cartesian plane. I'll come to my Cartesian plane, something like this. There you go. On my Cartesian plane, I'm drawing something like that. Label the y-axis, label the x-axis. Right, I'll start with the x-axis. There is -3, there is -2, there is -1, there is 1, 2, then 3. Right, going upwards, I'll use 2, 4, 6. There is 2, 4, 6, 8, 10. Okay, right. Now from there, plot -3 and 9, just like what we did in the previous, -2 and 4, -1 and 1, then 0, 0, 4, then 9, something like that. Then I'm going to join this using a freehand. That's a smooth curve. This is the graph F. That is the graph F. Right. Now I'll come to the next one, which is g of x. If you look at g of x, this is what? X plus a1 all squared. Okay, x plus a1 all squared. Meaning to say wherever there is x, I'm going to put -3 for the first one. -3 plus 1, you get -2. All squared, you get a 4. Right. You get a 4. -3, that you get a 4 there. -2 plus 1 is -1. All squared, you get 1. -1 plus 1, 0. 0 squared, that will give you 0. 0 plus 1, that's 1. All squared, that will give you what? 1. 1 plus 1, 2. All squared, that's 2. 2 squared, that is 4. Right. 2 plus that, that's 3. 4 squared, that's 9. 3, that is 4. 4 squared, that is 16. If I'll come and plot that, -3, you give, it will give you 4. -2, it will give you y is 1. Then -1, -1 and 0. Right. Then 0 and 1. Okay, I can see that 0 and 1. 1 and 4. 1 and 4. Then 2 and 9. 2, 9. Then 3 and 16. 3, 16. I'll come and put my 16 somewhere there. Okay, I'll join this. There you go. There you go. There you go. It turns there. Okay, right. This is your graph. That's your graph. Now, if you look at this graph, so remember it's a parabola. It's supposed to be symmetrical about the origin. Is to also come to 16, which will be now your parabola, something like that. Okay, now if I try to compare these two graphs, you realize something very, very important. If you look at these graphs, you can see that with the original graph, the turning point was at 0, 0. With this one, the turning point is now at -1 and 0. Meaning to say this g of x is a result of f of x shifted 1 unit to the left. So what am I observing? If I compare x squared and x squared plus 1 all squared, which is g of x, you can see that wherever there was x, you are now adding 1. And as long as you are adding 1 inside that bracket, the graph is going to shift to the left. So if I want the same graph g of x to move 2 units to the left, I'll just come and say x plus 2 all squared. It will move 2 units to the left. If I want it to move 5 units to the left, I'll just come and say x plus 5 all squared. Wherever there is x, remember this was x squared. Wherever there is x, if I come and say x plus 5 all squared, this graph is going to shift 5 units to the left. That's an important discovery. We did that in our lower grades. Right. Now let's look at our g of x, our h of x. In our h of x, this is now x minus 1 all squared. The other one was x plus 1. It moved 1 unit to the left. Let's see if this is x minus 1 all squared. You take negative 3, you plug it there, it becomes minus 3 minus 1, which is negative 4 all squared. That will give you 16. Negative 2, negative 1 all squared, that will give you 9. Negative 1, negative 1, that will give you negative 2 all squared. You get a 4. 0 minus 1 all squared, that's 1. 1 minus 1, that's 0. 2 minus 1, that's 1. 3 minus that, that's 2. 2 squared, that's a 4. Right. So if I'm to plot that, this is negative 3 and 16, negative 3 and 16, negative 2 and 9, negative 2, 9, right, negative 1 and negative 1 and 4, negative 1, 4, then what, 0, 1, which is that one, then 1, 0, which is that one, 2 and 1, yes, 2, 1, then 3, 4, there you go. So if I'm to join that, that will give you something like this. That's your parabola. Change there, goes up. Right, since I want sin, extend it to come to 16 as well. Right, but the most important thing is to compare these two graphs. The turning point of this one is now 1, 0, but the original one, the mother graph, was turning at 0, 0. So you can see that h of x is a result of f shifted 1 unit, shifting 1 unit to the left, 1 unit to the right. Okay, so whenever I'm subtracting inside that bracket and I go and say x minus 2, it means the graph is going to move 2 units but going to the right. If I say x minus 5, it will move 5 units to the right. So it is very, very important to know that whatever generalization that we are speaking of now, it is the same generalization that applies to all our functions. All our functions. If you go to a hyperbola, if you go to a parabola, if you go to an exponential graph, once you are subtracting wherever there is x, the graph is going to go to the right. Once you add, the graph is going to go to the left. So in terms of conclusion, before I give you an example, I'll come and say conclusion. P shifts the graph either to the left or to the right. Okay, now it is important to note that if f of x is now replacing wherever there is x with x plus 1, the graph, or let's say x plus p, the graph moves where p units to the left. Of x is now equal to x minus p. Wherever there is x, I'm now substituting x minus p. Then the graph shifts or moves p units to the right. Okay, right, that's important conclusion there. Let's look quickly at examples. Let's look at examples. Given that f of x given that f of x is equal to 2 all over x plus 1. Shift f of x 2 units to the right, and right, the resultant function g of x. So when I'm solving that, I know that the resultant function is g of x. So g of x is equal to f shifted how many units? 2 units to the right. When you are going to the right, you'll be subtracting where x is. So wherever there's x, you are going to subtract 2. So it means the resulting function becomes 2 all over. Wherever there's x in f of x, it becomes 2 plus a1. This is the resultant function. Okay, let's look at my second example there. Example 2. Example 2 is equal to 2 cos x minus 30. 2 cos x minus 30. Shift f of x 60 degrees to and to downwards. Okay, there you go. You are not given the resultant function. So what am I going to do? F of equal to f of x shifted how many units? But to the left. So whenever you're going to the left, wherever there's x, then 2 units down, so it's minus 2. So you are going to go back and say, what was your f of x? It was 2x. Where there is x, I'm now at 60. Then there was minus 30 inside the bracket, right? Minus a 2 for it to go down. So it means the resulting function becomes 2 cos x plus 30 minus a 2. You've shifted the function. How many units? 60 degrees to the left and 2 units downwards. Okay, right. Now, that's how you shift a function. That's how you shift a function horizontally, either going to the left or going to the right. Okay, right. Now let's look at the next form of transformation. Right, the next form of transformation is reflection. Reflection, reflection of a function. Right, reflection of a function. There are 3 types of reflections that we are going to basically look at in general. The first one, it is a reflection. Okay, let me just write it in continuous. There are 3 basic types of reflection that we are going to be focusing on. Right, the first one, A, it's a reflection along the x-axis. The second one, it is a reflection along the y-axis. Remember, the y-axis is also called x equal to 0 line. This is also called y equal to 0 line. Then the last one, it is the reflection. It is the reflection along the line y equal to x. Okay, right. Okay, right. I'm going to start with reflection A, which is reflection along the x-axis. Reflection along the x-axis. I'll just take you back to grade 9 and say whenever you are reflecting a coordinate. So I'll start with reflecting a coordinate or a point on the Cartesian plane. When I'm reflecting a coordinate along the x-axis. In grade 9, we're using the rule which says what? When I am reflecting, you've got a Cartesian plane like this, and I've got point A somewhere there, and you reflect it along the x-axis. It means the distance from there to there is the same as the distance from there to there. This will be A prime. So if this is x, y, in this quadrant, it means this will be x minus y. So the rule was x, y as a coordinate is now mapped onto x negative y. Remember, this was the first quadrant. Both of them, where A is, both of them they were positive. But when you go to A prime, you can see that that is the fourth quadrant. Y is what? Negative. But x remains x because that's a vertical line. The x coordinate A and the x coordinate A image, they are the same. So the rule that we're using in grade 9, xy is now mapped onto x minus y, such that if I'll do an example there quickly, you were saying in grade 9, reflect, that's a question, reflect A with coordinates 3 and 2 along the x-axis or the line y equal to 0. Right. Now, you were saying x using the rule is mapped onto what? X negative y. That was the rule. So if your A is 3 and 2, it means the A image becomes what? 3 and minus 2. The y coordinate is supposed to pick a negative. That's what we did in the lower grade. That was reflection of a coordinate. Now I'm coming to reflecting a function. Right. That was reflecting a coordinate along the x-axis. Right. Now I'm coming to reflecting. There is a difference between reflecting a function and reflecting a coordinate. Reflecting a function along the x-axis or line y equal to 0, something like that. Okay, right. Reflecting that. When you are reflecting along that line, what we are going to do is, remember, using the same argument, if I've got my Cartesian plane like this, and this is my A with coordinate x and y, but remember, y is the same as what? F of x, because I'm now reflecting a function. That's why I'm writing it in functional notation, right? If I reflect it along the y-axis, it means my A image is now there, where x is now the same as what? Negative y, but y is what? F of x, something like that. So the rule that we use to reflect a function simply says what? f of x, the original function, will be now mapped onto negative f of x, something like that. That which was y is now negative y. Okay, so in terms of conclusion on this, we can say when reflecting along the y-axis, when reflecting along the x-axis, right? In terms of just a quick conclusion, we can simply say when reflecting along the x-axis, one should uh, effect the given function with a negative. You negate the whole expression, or you effect, we can simply say, or multiply the given f of x with a negative. So once you are given a function and they say reflect this function along the what? The x-axis. Let me just give you a quick example there. Right, look at this example. Look at this example. You are given that f of x is equal to 2 to the power of x minus a 2. Reflect the function f of x along the x-axis, write the resultant function as g of x. Right, look at this. I've got a function g of x. This is my resultant function, but this is a result of f being reflected along the x-axis. And we said whenever you are reflecting along the x-axis, you are supposed to effect or multiply f of x with a negative, something like that. So you just go to your f of x and say 2 to the power of x, multiply everything that is called f of x with a negative. That will be what? Negative 2 to the power of x plus a 2. That will be the function g of x, which is a result of f reflected along the x-axis. So that's the technique that we are going to use. Once they say reflect along the x-axis, one should not stress there. Just go to the function f of x which is given, multiply that f of x, the whole of it, with a negative. That's as good as reflecting it along the x along the x-axis. Any function that you can, be it a trigonometric function, be it a hyperbolic function. Let me just quickly give you an example. The example number 2, example 2 there, given that f of x is equal to x squared minus x plus a 1. Reflect f along the x-axis. Simple, or line y equal to what? 0. Someone will just come and say f, in this case you are not given the resultant function, is equal to negative f of x. So you just go to your f of x, you multiply. That's what we mean when we are saying effect it with a negative, which is negative x squared plus x plus 1. That will be the new function f of x after being reflected. Sorry, this is supposed to be a negative one because we've multiplied a negative with a positive. Okay, that is how you do. This is how you reflect along the x-axis. Okay, right. I'm now going to reflection along the y-axis. We're still under reflection. Reflection along the y-axis. Okay. Right, reflection along the y-axis or the line x equal to 0, something like that. I'm trying to reflect along this line. I'm going to start with reflection of coordinates. Then I'll come to reflection of functions. Reflection or reflecting a coordinate or a point along the y-axis or the line x equal to 0. Okay, right. If you go back to your lower grades, you were taught that if I've got a point A there, call it x, y, and you reflect it across or along the y-axis, it means the distance from there to there will be equal to the distance from there to the image, which is A prime. Okay, but what is happening? In the first quadrant, both A and y they are positive. But in the second quadrant, x is now picking a negative and y remains the same. Okay, so we were saying the rule on this one, the rule of transformation simply said x, y is being mapped onto negative x, y, something like that. This was the rule that we were using in our lower grade, that was grade 9. An example, a quick one there, we can just say, given that P is with coordinate 4 and minus 3, something like that. Then reflect P along the line x equal to 0. X equal to 0 is the y-axis, so someone can just come and state the rule and say the rule says negative x, y, something like that. So it means if your P is 4 and minus 3, this P prime, the image of that becomes minus 4 minus 3. You've reflected. That's what you're doing in the lower grade. Right. Now I'm looking at reflecting a function along the y-axis. Right. Now when I'm reflecting a function along the y-axis, the general rule says from your grade 11, when reflecting, just from the observation that we had on coordinates, when reflecting when reflecting a function, if this is now a function, when reflecting a function along the y-axis, simply replace x with negative x. So what that means is f of x becomes f negative x. Wherever there is x, you are now substituting with negative x. As simple as that. That's if we're time, we're going to draw all things and try to deduce where this is coming from. But the most important thing is the generalization that we got from grade. So example number 1 there, let's look at how I would apply this, given that given that f of x is equal to 2 to the power of x minus a 3, reflect f along the y-axis and the resultant is of x. Right. So it means h of x I'm now solving is a result of f reflected along the y-axis. Whenever you are reflecting along the y-axis, wherever you see x in the given function, you replace it with what? Negative x. So you go back to that and say this is now 2x, but this is now negative x minus a 3. Then it means I've reflected along the y-axis. As simple as that. Look at example number 2. Very simple. Um, reflect equal to 1 all over x minus 1 plus 2 from the y-axis. If I'm reflecting along the y-axis, this is going to be what? Um, f of x is going to be equal to f of x. Okay. Okay. Let's look at this example. Allow me to write it there. Example number 2. Sorry about that. Example 2 says reflect f of x equal to 1 over x minus 1 plus a 2 along the y-axis. Okay, I'm going to reflect that along the y-axis. What I know is f of x, I'm not given the resultant function, so I'll call it f of x, is equal to negative f of x. So this is as good as just 1 all over negative x. Where there's x, I'm replacing with negative x plus a 2. Someone can further on simplify this and say 1, let me factorize the negative. That would be x plus a 1 plus a 2. Right, now that will be negative 1 all over x plus a 1 plus a 2. There you go. That will be the resultant function after the transformation. Okay, right, that's how you reflect along the y-axis. Right, I'm now looking at reflection. Reflection along the line y equal to what? X, y equal to x, something like that. Okay, reflection along the line y equal to x. Right, reflecting a coordinate from your lower grades. Reflecting a coordinate along the line y equal to x. In the lower grades, the rule that we're using to reflect a coordinate along that, it will be xy, and you were told that you just simply interchange variables, then that's a reflection. Say, for example, given that B is with coordinates 2 and 3, something like that. Reflect B, point B, along the line y equal to x. So you come and say B is with coordinate 2 and 3. This is going to be mapped onto B prime, the image, which is now 3 and 2. So whenever you are reflecting along the line y equal to x, you interchange variables. Okay, right. Now let's look at reflection of a function. Reflecting a function. Reflecting a function along what? Reflecting a function along y equal to what? X. Okay, right. Now when you are reflecting a function along the line y equal to x, allow me to write there, reflecting a function along the line y equal to what? X. Right. Once they say reflect a function along the line y equal to x, remember, this means you are supposed to get the inverse of that function. This is as good as just get the inverse. Remember, when there were coordinates, we just interchange variables. But when it's a function, when reflecting along a function along the line y equal to x, one should always remember that you use the steps to get the inverse of a function. Use the steps of getting the inverse of a function. What were the steps? Step 1, interchange variables, just like what you did with coordinate. Interchange variables. X becomes y becomes x. Step number 2, make y subject of the formula. Okay, right. Then, where necessary, replace f inverse with y. Okay, right. Let's look at this example. So, some examiners, instead of saying get the inverse of this function, they will say reflect this function along the line y equal to x. Once someone says reflect a function along the line y equal to x, you should always remember that they are looking for the inverse of the function. So you take the process of getting the inverse of a function. Now look at this. Given that um, f of x, given that f of x is equal to 2 to the power of x minus 1. Reflect f along the line y equal to x and write the resultant function as g of x. Okay, now once they say reflect along the line y equal to x, great hopes, they are as good as just saying determine the inverse of f of x. So I'll come and say y is equal to 2, x minus 1. So if I'm to get the inverse, interchange variables first, minus 1. Right. Then the next step is make y subject, that is x minus 1 equal to 2 to the power of y. How do I make y subject? Change from exponential to logarithm. This becomes the number, this becomes your exponent, and that is the base. So I'm going to convert it. This becomes what? Y is equal to log of the number, which is x minus 1, put that in bracket because all that represents the number. The base remains the base, which is base 2. So it means this is what? The inverse. Write it in terms of g. So it's g is equal to log x minus 1 base of 2. That is the reflection of that function along the line y equal to x. Okay, lastly, I'm now going to look at other key things in your grade 12, which is reflecting of coordinates or transforming coordinates using the following rules. Okay, transforming coordinates using specific rules. Okay, right. So let's just look at that. Then that will be it on this class. Okay. Transforming or transformation of coordinates using the following rules. The following rules. Okay, right. There you go. All right. Now look at this. The first one says 2. The first one, call it a 2 times f of x. If you are asked to transform a coordinate using this rule, this is 2 times f of x. Remember, f of x means y. So it's as good as just multiply y with 2. Okay, so this means multiply the y coordinate by 2. Y coordinate by 2. Say I've got a as my coordinate with 3 and 2. Then you are transforming it using 2 times f of x. This becomes a image, which is 3, 2 times 2. So a image becomes what? 3 and 4, something like that. Right. Look at this one. B f right. F evaluated at 2x. This means divide each x coordinate with 2 or divided by 2. So if I'm given something like b with coordinates 4 and 3, something like that, it means b image becomes 4 divided by 2 times a 3. So b image becomes 2 and 3, something like that. Okay, that's very, very, very common in your exams, right? When you are given f x over 2, once the parameter is inside the bracket, it affects x. Once the parameter is outside the bracket, it affects y. So it means this one, you multiply x coordinate by 2. Okay, so if I've got something like c, which is 1 and 3, this would be what? C image, which is 1 times 2, which will give you what? C image is now 2 and 3, something like that. That's how you reflect. So when you are dealing with a parameter which is inside the bracket, when it's multiplying, you divide. When it's dividing, you what? You multiply. Okay, that's that. Okay, let's look at the next one. You are given something like this, D, which is um, 2 times f of x plus a 3. If you look at these two parameters, 2 and 3, they are outside the bracket. So they are both affecting the y coordinate. So it means what? You are supposed to go and what? Multiply the y coordinate by 2 and add to the y coordinate 3 units. So what that means is, if I've got something like this, this is 2 a with coordinates 2 and 3, sorry, it means its image becomes 2. Remember, x coordinate is not affected, but to the y coordinate, which is 3, you multiply it by 2. To whatever answer you're going to get, you're also going to add what? 3. So this will be what? Equal to a image is 2, that time that is 6, that will be 9, something like that. Okay, right. That's the same thing. The last thing is, say you are given f x plus a 1 minus 2. Simple. This negative 2 denotes, or it stands in for y. It's going to affect negative 2 affects y. X plus 1 affects what? X. Right. So in this case, what are you going to do? Remember, x plus 1 simply means you go to the coordinate and you add 1. Remember, this is a coordinate. Add 1 to the x coordinate and what? You are going to subtract 2, subtract 2 to y coordinate. Very, very important. Thank you for that. Hope and pray you found this helpful. I'm going to give you an activity on this. Um, I'm going to give you an activity on this. But the most important thing is to make sure that you master these types of transformations. Very, very important in your exams. I hope and pray that you've mastered them. Some of them, or most of them, they were pure review of what we did in our grade 10 and grade 11. So I just wanted you guys to make sure that you re-embrace these things, so that when you are in an exam, you will not be intimidated by these transformations. You actually be perfect, and you actually be applying this knowledge as something that you develop from your lower grades. Thank you so much, grade 12. Let's meet in the next lesson. Bye.